Hi, Math 30-1s. We're just going to continue on today discussing identities with trig functions, equations. So last day, the way they start this lesson is just taking a look back at all of the sum and difference identities we learned last day. Okay, so you can see there are 6 there. Sum and a difference identity for all of sine, cosine, and tangent. And again, there's no need to memorize those. Those are always provided for you on a formula sheet or in the lesson, as you can see here. Today what we're going to talk about are double angle identities, and on this page, or the remainder of this page, we're going to take a look at proving or showing that the double angle identities are in fact identities, okay, or how we create them. You will not be tested on this, okay, so on the remainder of this page you're not tested on it. It's just more some calculations to show you how we can create them. What's more important for you with these double angle identities is what we're going to do on the second page, okay? So just to start, it says, consider the statement sine of 2a is equal to 2 sine of a. First off, determine whether or not this statement can be true for angle A being pi over 6. So again, all we're doing at this point is seeing if this is true based on one specific angular measure, which is pi over 6, okay? So when we do that, remember, we're going to talk about the left side and the right side separately. So the left side will be the sine of 2 times A, and in this case, A is pi over 6. Okay, so when I do that and I multiply by 2 by the pi over 6, the 2 over 6 reduces to 1 over 3, so this is equivalent to the sine of pi over 3, okay, which will be equal to root 3 over 2. With the right-hand side of the equation, okay, we are going to have 2 times the sine of pi over 6, okay, so this will be equivalent to the following. 2 times the sine of pi over 6 will be 1/2, okay, and that is equal to 1. So when you take a look at that, you will see that the left side is not equal to the right side, okay? The statement cannot be verified. So when it says, what can we say about the statement sine of 2a equaling 2 sine of a? All that we say is that it's not true or it cannot be verified, okay? However you prefer to word that. To develop an identity for sine of 2a, okay, we use the sum identity for sine of a plus b. So that's why they provide it for us at the top of the page so that we can refer to it quickly if we're not, if we don't have it memorized or if we are unsure of where to find it really quickly. So the first thing it does, it says, explain how the sum identity sine a plus b can be used to determine an identity for sine of 2a. Okay, well, the first thing is that if I have 2 a's, okay, 2 of anything, okay, I can add the same thing to itself to get to 2 of them. So 2a could be written as a plus a, right? So then all I do is I go into the identity for sine of a plus b, okay, and I'm going to replace the b, okay, with another a. So I'm going to have sine of a plus a is what's going to basically happen. Okay, so that's what I'm going to do. So what we're going to write here is just what we're going to do in the next step. We're going to replace the b by an a in the identity for sine a plus b. Okay, so that's what I'm going to do. So the sine of 2a then, like this, sine of 2a is equivalent to the sine of a plus a, right? Because a plus a is 2a. But now I have something that looks very similar to sine of a plus b, but both my angles are going to be a. So it comes out to be sine a cosine of a plus cosine of a sine a. So what you have there is you have 2 sine a cos a's. I have 2 of the same thing. Okay, both of those terms are sine of a times cos of a, so I have 2 of them. Okay, in the next one it says prove the double angle identity cos of 2a is equal to cos squared of a minus sine squared of a. So again, I am talking about the cos of 2a, just like up above, and I can rewrite that as the cos of a plus a, right? A plus a is 2a. Now this is like a plus b, but I'm going to have a in both spots, okay, instead of an a and a b. So this is cos a cos B, which again is another A, minus sine A, and then sine B, which again in this case that other B is an A again. So what I have is cos A times cos A is cos squared of A, minus, and sine of A times sine of A is sine squared of A. Okay, so there's your double angle identity for cos of 2A. And then the last one, okay, they want you to do the same thing for tan of 2A. So the tangent of 2A, okay, could also be rewritten as tan of A plus A. Okay, and again, I follow tan A plus B, but I use A for both angle expressions. So this will be tan of A plus tan of A. Okay, and I'm just following tan of A plus B from above. And then 1 minus tan A, tan A. Okay, so what that gives me is, in the numerator, I have 2 tan of A's. Okay, and in the denominator, I have 1 minus tan squared of A. Okay, so what I've done is I have come up with, okay, the double angle identities for sine, cosine, and tangent. Okay, and you'll see those on the next page, okay, as we turn the page under the heading double angle identities. Now, you'll see that sine of A and tan of A have one double angle identity there. The cos of 2A has 3 different ones, okay? So you can see these 3 here, and they all come from the fact that I know sine squared of A plus cos squared of A is equal to 1. So what happens is that I take the first one that they give me, okay, and in either one of them, I'm going to replace either the cos squared of A or the sine squared of A with 1 minus the other trig identity or expression, and then I get one of the 2 that follow, okay? So what I mean by that is if I take the first one, for example, right, cos of 2A equals cos squared of A minus sine squared of A, okay, I'm going to replace the cos squared of A with 1 minus sine squared of A, and then minus another sine squared of A. So this will give you 1 minus 2 sine squared of A, okay, which takes you down to the third one. Had I replaced sine squared of A with 1 minus cos squared of A, I would have ended up with the second one there out of the 3, okay? So you're going to use the first one most often, but you will use the second and third ones for cos of 2A every so often. So just be aware that they exist and that you don't need to know them. You can always create them, okay, by, like I showed you on the right-hand side there, replacing either cos squared of A or sine squared of A with 1 minus the other trig expression from up above, the Pythagorean identity. Okay, so now let's get into some questions here. It says, prove that the identity 2 tan of x over 1 plus tan squared of x is equal to sine of 2x, that it's valid, and then state the non-permissible values. So again, that we're going to be taking a look at the restrictions for the denominator. So to prove that this is true, okay, I'm going to take that left-hand side and work on it because we always take the more complicated side and start to work on that. So what I'm going to do is take the 2 and tan of x. Remember, we always try and write in terms of sine and cos if we can. So I have 2 sine of x over cos of x, that's the numerator. And in the denominator, I'm going to write secant squared of x. Now, where does that come from? Well, that's an identity, okay, from your identity sheet. 1 plus tan squared of x is equal to secant squared of x. Okay, so as I move now along here, in the numerator, I'm going to have, so 2 sine of x. So 2 times sine x cos x gives you 2 sine x over cos of x. All over secant squared of x, which can be written as 1 over cos squared of x. Now, why would I do that? Because what that allows me to do is the following. It allows me to now, instead of dividing by 1 over cos squared of x, I can multiply by the reciprocal, which will be cos squared of x over 1. So what happens at this point now is the squared there cancels with that cos of x here, leaving me with, in the numerator, 2 sine x, 1 cos x, and then the denominator, the number 1. Okay, so 2 sine x cos x, and if you take a look up at your double angle identities we just learned, 2 sine x cos x is equivalent to the sine of 2x. Okay, so which is, in essence, right, what we have going on the right-hand side, right? The right-hand side is the sine of 2x. Okay, so I don't have to do anything to that right-hand side. Now, I need to discuss the non-permissible values or the restrictions. So what's a denominator here that can possibly equal 0? Well, cos of x. Now I know in the denominator here I have secant squared of x and cos squared of x, but when I square values, okay, we can't make them equal 0. There are no denominator restrictions here in this case. So only cos of x is what I need to worry about. So I cannot have cos of x equals 0. Okay, I do not want that, which would mean x cannot be equal to, okay, pi over 2 plus pi n. Okay, remember that is our expression when we are dealing with cosine. Okay, when we're worried about cosine equaling 0, there's the expression. Okay, pi over 2, and then every pi radians, or in degrees, it would be 90 degrees plus every 180 degrees, okay, if you were discussing that or thinking about it in degrees. Class example 2 says, use the identity sine of 2a equals 2 sine a cos a, with a replaced by 3x to determine a double angle identity for the sine of 6x. Okay, so here's what they're saying. I'm starting with the sine of 6x. Okay, that's what I have. If I wanted to write that as a double angle identity, well, that would be the following. It would be the sine of 2 times 3x. Okay, 2 times 3x is 6x, is it not? But what I've done here is I've written it as a double angle identity. It's the sine of 2, and this whole thing in this case is like your a. Okay, you're using 3x instead of a, which is what they're telling you to do. So when I take sine of 2a, you take a look at the double angle identity for sine, okay, that would be 2 sine of a, and in this case my a is 3x, so sine of a and cos of a, and again a in this case is 3x like so, and there you go. So, you know, you just remove the brackets, you don't have to have them there, okay, it's fine if you do, but this is just 2 sine 3x and the cos of 3x, and there you go. So using that same idea, they want me to write cos of 10a, this is in B now, as a double angle identity. Well, cos of 10a can be written as the cos of 2 times 5a, can't it, right? So that's the cos of 2 times 5a, which if I follow my double angle identities could simply just be the cos squared of a, your a this time, right? Here's your a. Cos squared of a minus sine squared of a. And again, I could have used one of the other expressions for double angles for cosine. Remember, we have 3, but I just used the first one, okay? Now, tan of x, okay, this one's interesting, right? Tan of x, there is no number in front of that x, but I could go like this. It could be the tan of 2 times, if it was a 2, I'd have to put a 1/2 in front of the x, so that 2 times 1/2 gives me that 1 that's sitting in front of that x, even though we don't see it. So now, this is like tan of 2, and this whole thing here is your a. So it's tan of 2a. So 2 tan of a, there's your a, half of x, all over 1 minus tan squared of a. And there's your a again, half of x. So there's your expression. You wrote it as a double angle identity. Now in class example 3, we're going the other way. Okay, they've written out the identity kind of in the expanded form. I'm going to kind of bring it back and simplify it a little bit. So what I have here is 2 sine of a cos of a. Those are your a's there. See how we have 4x repeated? So when you have 2 sine a cos a, that's the same as sine of 2a, and your a is 4x. So this can be simplified into the sine of 8x. Okay, in the last questions we went the other way. This time we're going this way, we're simplifying it. So in B, I have cos squared of a, sine squared of a. So the 1/2 a is like your a in this question. That's your kind of like your angle. So that could be the same as the cos of 2 times a, and your a in this question is 1/2 a. So 2 times 1/2 is 1. So this is just cos of a. Okay? Similar to the tan of x question we just did up above. Now C, okay, is a tricky one. Okay, you probably want to put a star beside this. So you can see I have sine of x, cos of x. So these again are your x's here, right? But what I really want, or what I think this should look like is this. 2 sine of x cos of x. So what was missing that I put in there is that number 2, right? That's what should have been there. So the reason it's not there is because I would have had to multiply that whole thing by 1/2. Okay, so this 1/2 times this 2 would have given me 1, and that's why there's a number 1 up here. Okay, so it would have been 1/2 times 2 sine of x cos of x. So what that means then is it would have been 1/2 times, so 2 sine x cos x is the sine of 2 times your x, which is this in this case. So when I do that, okay, it simplifies to 1/2 sine of, and 2 times 5/2 is just 5x. Okay, and there's your simplified expression. Okay, single trig function. And that's it for today. Okay, there's not a ton of new stuff to learn. You just, again, have to learn a new set of identities that you're going to use and work with, be able to locate them and manipulate them from your formula sheet. Any questions or concerns, you guys get a hold of me and I'll get